Hello everybody. We apologize for the delay due to technical reasons. There are always technical problems, as you know, mainly in this time where we want to present you the presentation online as well as for local participants. My name is Martin Saska, and I'm going to introduce this workshop with let's say more general talk on autonomous multi-robot systems we are developing here at Czech Technical University in Prague. My presentation will be focused on systems designed for inspection, because this workshop is mainly on inspection. The main content of the workshop is indoor inspection, which means flying in GPS-denied environment without GPS, with onboard sensors only. And but I will, in my more general talk, introduce you also some projects we are working on outdoor inspection where we can use GPS, but we will be focused on application where the precision of the GPS is not sufficient, and we have to still rely on onboard sensors to be precise enough to get the required information and to achieve fully autonomy. So our systems, which I'm going to present to you, and also my colleagues later on, are fully autonomous. So you don't need, in fact, any operator to be present. Usually we have a safety pilot in most of the industrial application, but that people are just carrying RC without touching it, and they are prepared to save the drone. But I have to say that now the system is robust enough that usually any input from the pilot is not bringing anything, any plus, and the system itself is able to solve most of the problematic parts of the mission. Let me also tell you a little bit about the workshop outline. So after my general presentation, there will be the main presentation of the project, which is financed by Ministry of Culture of Czech Republic, which is focused on historical building inspection. This will be done also in English. Then there will be some real demo indoor, also commented in English, and Czech participants are invited to listen to a short overview in Czech. Will be also provided for media, where we will provide a brief summary of the work in this project and also in some others. So this will be 1 hour slot at 12. So who is interested in Czech summary, just let us know. We will provide you a link. And after this demo, there will be presentations of some participants of the workshop that are not from our group. And after that, there will be a discussion on future streams of inspection by aerial robots and robots in general, indoor, outdoor, mostly focused on fully autonomous systems. So let me start introducing my group. We are now more than 30 people working mostly on aerial robots. We have also some projects with like a cooperation of drones and ground robots or drones and boats, but our main interest is aerial robots and even groups of cooperating aerial robots. So we are usually focused on applications where one drone is not enough, and we need to employ a team of cooperating drones. And in our projects, the drones are used mainly to cooperate tightly. So it means that they are going to solve a task that is not solvable by a single vehicle, and the cooperation is required. So the motivation of this deployment of multiple robots is not only to save time, to cover more space, or to do multiple tasks in parallel, but we are focused really on the task where you need to have several drones flying close to each other carrying an object, for example, together. Or as you will see in the next presentation, providing a task where one drone is carrying a camera and other drones are carrying a light, for example. So all these tasks could be potentially done by a drone, but with a lot of limitation, like the drone would need to be really large, carrying a really large equipment, very powerful, very dangerous. But using multi-robot systems, we can solve this with higher safeness and even reliability. Besides this industrial project, I will also briefly touch some research projects we have and also some competitions, because they are tightly related to this inspection, as I will show you a little bit later. So at the beginning, let me start with the control architecture of our system, which is the core. And if you are interested in using this system, everything is fully open source. My colleagues will provide you links and even some guideline and information how to use our system. So if you are a beginner at the autonomous drones, you can start with that. The system is designed to be very general. So in fact, we are now working on maybe 15 different projects in completely different robotic domains, all related to aerial robots, of course. And this core system is used in all of them. So if you have a very different project, then is one of these I am going to present, still, you would be most probably able to use the system and build on that. We have now more than 300 registered active users of the system from tens of different robotic laboratories or even companies. The components provided are here in the pictures you can see. So the base, so there is a high-level mission and navigations block, which provides you high-level commands for the drones or for multiple drones even. Usually the output of this block is a desired reference, which is then tracked by a tracker. So you can see it as a desired trajectory or task to follow by drones. Then there is a controller in multiple layers. We are using embedded autopilot PixHawk, but our system could be compatible with any other autopilots. Currently, we are also in some project moving to other autopilots if customers require it. So this is possible, but in the basic open source version, it's done for PixHawk. Another contribution we did is state estimator, which is using multiple different sensors. So you can attach to your drone a large variety of sensors for drone localization. And this is fused together in this state estimator and used in the feedback control. So this is the state estimation and sensor fusion system. So as you can see here, we have a set of Kalman filters, which are used to fuse these information from different sensors. And we have found that it's really important to rely on multiple different sensors, even in a single mission, because from two reasons. Of course, you can have a failure of a particular sensor, or there are sensors which are better in different environments. So let's suppose that you are flying in a church, which it will be seen later on, and a proper sensor for using in the church is a 3D LiDAR, as you will be seeing. You can use also camera, for example. In most of the cases, it will work nicely, but you may get in some places in the church where the environment is symmetrical and you don't have enough information about the height estimation, for example. So let's imagine that you are flying in a chimney or any hall which is kind of empty of artifacts in the church. And then it's difficult to estimate the height of the drone. So we have to fuse another sensor for height estimation. or you may fuse a camera. So it's up to you which sensor setup you will use, and the system will take care of it and fuse them together. And this will be used as an input of model projective control scheme. We have different controllers, or even you can use your own controller if you have, and plug it here. And as I said, the system is really modular. So based on your application, you may choose different sensors. Of course, always there is a PC on board. So these sensors are connected to a control, like a PC is the brain of the drone. We are in most of the cases using Intel NUC PC, but we have also some industrial modifications. So the system is general from this point of view as well. In some applications, you can use GPS, RTK GPS for flying indoor. You don't need to use this. So as I said, it's really modular. So after this brief introduction into the system, let me show you now a little bit more fancy pictures and videos, because I know that not all of you are roboticians. So some of you are already lost after these 3 slides, I know. So let me put you back, show you some applications. These are motivated by the MBZ RSC competition in Abu Dhabi. I'm going to show you these because it was a real beginning of our story of having fully autonomous drones flying in different environment and in like a real world environment. At that time, like 5 years ago, there was a lot of stuff available for autonomous drones, but most of them were designed for laboratory conditions. And we have found, and not only us, but the community itself, that flying in real world conditions is completely different story. You cannot control your environment. You have to, your system must be robust enough to fly in the real conditions, in the current conditions that are already there. And this was, in fact, a motivation of this competition to design a system which is being placed in the conditions which are given by the organizers, not by the team itself. At that time, we have found that testing of the system in even most complicated environment is necessary. So we are usually flying, as you can see here, in very demanding environment with natural conditions like a strong wind, strong light, wind gusts, dust from the sun, and being able to design and tune the system for such a difficult condition. Once you are going back to maybe simpler conditions, your system will be more reliable. So this was an important lessons we learned at the time. And we have been starting and building the general system. I'm going to present you, and also in the workshop. Yeah, so let me just briefly skip these first trials of autonomous drones we have done, in fact. So one of the trials at the competition was autonomous landing on a car. So it's a bit far from the inspection, so I will not spend much time here. I just have to say that we are second in the competition, and we were able to fully autonomous localize the drone, the car, the landing pattern on the car, and land. But still, we are using some techniques which are developed here for this project, because the landing on the car had to be very precise, and we had to react on the environment in real time. So at that time, we have designed the MPC controller to be able to estimate to predict the trajectory of the drone, but also of the car itself, and to find an optimal trajectory to approach the car. The second task was fully autonomous carrying of objects from unknown locations. And the task was done by a team of drones. So in fact, this was the first real system we have designed of cooperating drones. So the task was done by 3 drones cooperating. They were sharing the same workspace. So we have learned a lot of lessons we are now applying in the industrial projects, such as the one we are going to present you today. This we call it NAKI project on inspection of historical buildings. Yeah, so I have to say that we have, at that time, we won this task at the competition. And based on the results, yeah, here this slide just to show you different conditions where we are flying. And we have this practice till now. So we do usually a lot of experimental campaigns in different conditions. Yesterday, late evening, I came from Pilsen, where we were flying in old brewery. It was really a dusty environment of old, not repaired building. So something even more complicated than flying in a beautiful church. We have also a lot of experimental campaigns in countryside, in forest. So as I said, this is, in our opinion, very, very important to fly in real conditions. Here I want to just show you briefly some success story of an industrial transfer of results achieved at the competition. So based on the system for autonomous landing on a car, we have designed a system for hunting drones for protection of airfields or another like critical infrastructure like power plants and so on. So the customer required to design a drone that is able by onboard sensors to detect a drone flying in the forbidden areas by onboard sensors. So very similar task as the landing on the car. Again, we have a camera, we have a LiDAR, we have whatever to detect the target, and we have to plan the mission in a way that we will approach the target, land on the vehicle, or capture another drone by a net. So here in this visualization, you can see how the drone is designed. So the drone is taking off a heliport where it's carried. It's flying into a location which is reported by an external localization system as a target position. Once the drone is close to the target, it uses local sensors only to detect the target and catch it into a net, which is on board. The net can be attached on board or can be shooted. So here there are some very old demos of the system which is able to detect the drone, the target by onboard sensor and shoot the net, as you can see here. Now there is a lot of modifications of the system and a lot of variants. We are using also a firmly attached net to the drone to have repeated trials, but the story around is the same. You have onboard sensors and you have to use your autonomy and onboard intelligence to solve the task. Yeah, this I may skip. Let's use another 5 minutes for another competition which was done last year. And there was also a lot of really important achievements we did, which were transferred or are being transferred into the industrial project, as is the one we are going to present you today. I will show you the connections. So in that competition, the tasks were totally different. One of the tasks was capturing of a flying object. So very similar task as the Project Eagle one I have presented you a few seconds ago. The second task was building a wall from bricks. So in this task, we are going even much further beyond the inspection. We have to manipulate with the environment and effectors. So the drone is again using onboard sensor, onboard intelligence to detect the target, approach the target. This is the same as for the inspection, where you have to fly to an object and provide an inspection of the object, and you have to do it precisely to have the precise information. But here we go beyond, because we have to catch the brick and place it properly to a wall to build a wall. And the last task was firefighting. And again, you can find a lot of similarities. In that task, a fleet of drones, so again, cooperating team of drones, were designed to detect a fire. So using an onboard sensor, it can be thermal camera, it can be any other camera. Similar as if you are doing industrial inspection. You have to detect the target, approach the target in a given position. So the position can be proper for firefighting, to put a stream of water on the target, on the fire, or it can be a proper position for making a picture, making a video. So the task is very similar. So we have again transferred a lot of stuff from this competition into an industrial application. So let me briefly show you some results, some videos. Again, not to bore, not to get people that are not with robotic background back to the game. Here you may see some pictures from the first task where the drone was designed to capture some targets like these balloons. Then there was another drone designed for capturing a flying object. As you can see here, we were able to catch a ball from another drone. Then the task with the bricks. This task we won. In the first one, we were second. So in this task, as I said, the drone was designed to catch the brick, as you can see here, and place them on a given location, where is the position of the wall, as you can see here. Again, the training was done in really difficult conditions, as you can see here. A lot of dust, a lot of wind, a lot of sun, which is not proper for vision, as you know. And then the task itself in the conditions of the competition was quite easy. So this was the reason why our system was much better than the system of other competitors. And the firefighting, this was a really complicated task. We had to solve multiple subtasks simultaneously with a team of 3 drones and 1 ground vehicle. So there was a facade fires. There were some fires located inside of the building. So the task was to fly inside and do inspection inside, because you have to inspect the room to find the fire. So it was again a very similar to most of the projects where we are doing autonomous inspection. Yeah, let me skip these. This slide is going a little bit farther from the inspection, so let me spend here only 1 minute, maybe. It's one of our main research interests. It's swarming. So it's a swarm of cooperation drones. I have prepared these slides just to show you where, again, the similarities with such a complex system. Because in this swarming, we are focused on GPS denied environment. We don't like so much GPS. Firstly, of course, that you can buy a lot of drones using GPS and like DJI platforms. So there is no need of further development and research if you are poorly using GPS. But we have found that there is a lot of applications where GPS is not available. If you have to fly in the forest, the GPS is really poor there. You cannot use it for control of the drones. If you are flying in urban scenarios close to tall buildings, your GPS is really bad. You have for sure experienced this using your GPS navigation in your car. If you are flying in the cities where are tall buildings, sometimes your GPS is in a different street even, which is an error of 100 meters. With drones, we must be much more precise. And also there are tasks where the GPS precision is not sufficient. If you want to fly close to each other by multiple drones, you cannot rely on GPS. If you need to fly close to objects, you cannot rely purely on GPS. You have to detect the object itself to be localized relatively to the object. And we do the same in the swarming, where we have to keep multiple robots together to keep a compact formation, compact swarm. And again, we are using a lot of technologies designed for the swarming, for industrial applications, like the one where my colleagues will present you some task of multiple drones doing inspection in churches. Here in this research project, we don't rely on communication. We have again experienced that if you have a lot of drones flying in the same environment, it's really difficult to provide fully connectivity. We have found that communication is really bottleneck. So in most of our systems, if possible, we don't rely on communication, or we are using the communication, but there is always a backup system for using the system, the autonomy without communication, probably with lower with lower performance, but still being safe. In the swarming, we have strictly decentralized system. This is again related with no communication. In some industrial applications, we have found that centralized system provides you better performance, of course. But there must be again backup solution in case of communication dropout, where you don't have the possibility to use a fully centralized system. And we want to design systems which are really scalable to achieve large swarms. Probably, I don't want to say hopefully, I don't know if it's a good or not, but we expect that soon there will be a lot of drones flying in the same workspace, even in our cities. Probably there will be drone taxi, there will be drone delivery. So there will be a lot of drones kind of cooperating, or at least coexisting. And we have to design systems that are able to take care of these situations safely, or even provide benefits of these multiple robots being placed in the environment and solve some tasks that are not solvable so far. And in this swarming, we are focused on flying in high density of obstacles. And again, this is exactly the field where we want to be. We don't want to fly far away from the obstacles, because for that you can buy DJI platforms for a few thousand €, and you don't need to have this fully autonomous. Once you are far from obstacles in open space with GPS, you can follow the GPS positions and you are kind of done. But if you need to do the inspection in an environment with obstacles, you have to take care of them. You have to localize yourself in such an environment and avoid the obstacles. So we have already tested our system in multiple inspection scenarios. We have been flying in the longest tunnel for cars in Prague. The tunnel was closed for maintenance, and during night we were able to do some inspection, as you can see on the first upper left picture. Of course, we are, as you will be informed, we are flying in historical buildings. We are also flying in underground. This will be the last project I will present you before really skipping into the inspection tasks. We are also able to fly in forest, as you can see here. We can do it even with a group of drones so this system is fully decentralized. They don't communicate, they only observe the other drones in the environment. So maybe this is the future. we cannot expect that all vehicles in the shared space will be communicating with each other. And most probably they have to have a system which is on board, which is using onboard sensors to provide information about the neighbors. And it may be to avoid them, so it may be sense and avoid system, or it may be to cooperate with them. Let's fly together, let's do a platooning, let's do or solve some tasks cooperatively. So now I'm going really close to the inspection. The last competition I'm going to present you here is Darpa Subterrane Challenge. And in this task, we don't have to do really inspection of the tunnels. We have to search for victims or search for object of victims in underground environment. But the task itself is very similar. We have to scan the entire environment to provide some information, to work with this information. The system must react on the information and must provide the results back to the control station. So in most of the components are almost the same. We have to fly without GPS. Underground, there is no GPS, obviously. In historical buildings, there is no GPS at all. We have to fly close to obstacles, which may be unknown. So in this subterranean challenge, they are unknown, all of them. The map for us is unknown, completely unknown. We are just flying there, and we don't know what is behind a corner. So the robots need to be really smart to fly in such an environment. In churches, we have a little bit better situation. We can map the environment before, but still, what we do is we make a 3D model of the environment, which is done maybe a week ago, the mission, or the same model is used in multiple missions in the same church. But it may happen that somebody will move something in the church. It is quite often. So the system must react on new obstacles. There may be some people even. So the system have to react on the changes in the environment. So again, we may reuse a lot of stuff from this Darpa Subterrane Challenge in the industrial inspection, which is indoor for churches or outdoor in one of our biggest projects on inspection of electrical infrastructure, which I will present you in a few minutes. So here, there are some very preliminary results we have achieved in the Darpa Subterrane Challenge. The first task was flying in a golden mine in close to Denver. Then we are flying in a coal mine. So the Darpa team is really providing various scenarios, various environment. So our system must be reliable enough, robust enough to work in these different conditions. It's a cooperation of aerial robots and ground robots. With this competition, we are cooperating with several groups here at the Czech Technical University, Faculty of Electrical Engineering in Prague. So we are responsible mainly only for the drones and helping with the system integration, but there are other groups that are strong with ground robots and also with aspects of the communications. So the drones are using a network which is built by the ground robots to provide better communication. We don't need communication for the flying, for the drone itself. The drone is fully autonomous, but we have to report back the information which is found. So we have to localize some victims or objects in the tunnels, and we have to report the position of these objects located. And for that, we are using the infrastructure provided by the ground robots. So these pictures are from the second or third deployment of the system in the Darpa competition. that task, the system, the drones and ground robots, and even some spiders and some, as you can see here, some creatures in our team were employed to scan. Here is a team leader, Tomáš Svoboda, head of our department. So at that task, the system was employed in a former nuclear power plant. I hope these are the pictures from that. If not, I'm mistaken, but this is not from that. It's probably a compilation of multiple. Yeah, so this was not the one. So it was in this, yeah, sorry. So it was in the urban circuit. So in that urban circuit, we were flying in a former or not finished nuclear power plant. So it was a real environment of a power plant. And the drone was designed to fly in there autonomously, map the environment, avoid the obstacles, and in fact, do the inspection of this unknown environment. So the task is even more difficult than the one we are going to present you today. As I said, the environment here was unknown. We even didn't know what type of obstacles can be present, what type of environment is there. Because as I told you, you may use different sensors for different environment. So some sensors are better for flying in tunnels, in chimneys. Some sensors are better to flying in large open space environment. And in this Darpa Subterrane challenge is combination of all of these. So now we are in preparation for the finals. We are flying to US in 1 month, roughly. So hopefully we will achieve a similar good results as we did in these sub-competitions. So now, finally, sorry for the really long introduction, we are going to the inspection. So here I'm going to present you a European project Aerial Core, which is it's a project coordinated by University of Sevilla, by a group of Aníbal Hoyer. It's it's a core robotic project. So in the consortium, you can find really big names in robotics in Europe. The tasks are really challenging. It's not only on inspection, it's also on maintenance of the infrastructure. So as you can see here, we are working on drones that are able to provide some parts of the electrical infrastructure, some bear to diverters, some even to help people to maintain the towers. So that there will be even some hybrid drones, combination of fixed wing and multi-rotor drones to provide longer endurance. We are more focused in the project on 2 tasks. One is this aerial co-working. It's really kind of science fiction task where the plan is to have a team. I hope you can't see this huge noise from workers here. So the task is to have a team of fully autonomous drones helping people climbing a tower. So there will be drones doing inspection. So the person on the tower can provide or ask drones to provide some information, for example, on some isolator, which is not visible from the position of the person. So the drone may provide a different point of view on the isolators or other parts of or components of the tower. The motivation is to provide more reliability or safeness for the human. Usually the human is not able or would need to climb into some dangerous position to see it from different perspectives, these components. So the drone can provide this information. Another drone is used to observe the human itself. The companies in this business found that there is still a lot of accidents. And these accidents are because people are not following the safety instructions or safety rules. So they require to have a drone spy, which will be spying the worker climbing the tower, providing a record of the activities done by the human, either for further investigation in case of the accident, or for kind of penalization of the worker or pushing the workers to follow the instructions, the safety rules. And finally, there is a third type of drone, which is really co-working with the human, providing a tool, for example, or part of the tower, helping to bring a big part of the tower to the human. So of course, you cannot expect that such a system will be deployed tomorrow. It's a really long way ahead of us, but most probably in future, we may see such complicated systems. So we have done already some preliminary research steps in this project. We have designed a multi-layer software architecture for cognitive aerial autonomous power line inspection. So again, the cognitivity is there in the fact that the drone is able to react on the environment. So there is a feedback which enable to change even the mission. So if there is, for example, new obstacle, the drone autonomously or the system autonomously may replan, avoid the obstacle, or even change the task completely. It's designed for a fleet of UAVs cooperating around the tower. So we have to deploy really multiple drones simultaneously, and they may cooperate. So it's very related also to the inspection of churches, where we are also deploying multiple robots. We have already some papers accepted as well. So here are some preliminary results of the task of human following and observation. And here in this approach, we are using a method which was primarily designed for inspection of churches. I have already mentioned it. In that task, one or several drones are carrying a camera, and one or several drones are carrying a light and providing lightening from a different kind of field of view. But my colleagues will tell you more about these techniques of smart illumination, so I don't have to spend time here. So you can see already that the system is able to follow a person, to see the person by onboard cameras. And it's cognitive enough to be able to react on the position of the person and the tower to fly safely around and do the task intended. We have tested it also in different environments, as in the forest, as you can see here. So this was the first subtask where we are involved in the inspection of power transmission lines. And the second one is long-range inspection. As probably you may know, so far, most of the long-range inspection of power lines is done by normal classical helicopter There is a crew of 2 people flying every day, the whole year. Only in Czech Republic, I know that there is a one helicopter flying, really doing that job every day. So it's really expensive. It's really boring for the pilot even. So even I have a personal experience. I attended one of the flights, and the pilot and the crew told me that it's really boring and they really wish to be replaced by autonomous drones so they can do more funny job. So the task of, or now the intention of most of the companies providing electricity, not only in Czech Republic, in all countries, are to design an autonomous system for inspection of power transmission lines by drones. There are some problems. Of course, the endurance of drones is not sufficient so far. The helicopter can fly for hours, small drones for tens of minutes, big industrial drone can fly maybe 1 hour, maybe a little bit more, but it's still not enough. Also, the speed of the drone is lower. So this was a motivation to design, firstly, a special platform with longer endurance, faster flying time, or using multiple robots to achieve the task. So for this project, we have designed a planner which is using multiple robots to plan optimal inspection trajectories to save time and to do the same job which is done by a big helicopter in hours, by small drones in tens of minutes. Another research we are doing in the project is on using signal temporal logic for planning of inspection trajectories. We tackle this problem as I may try the second video as well. We tackle this problem as an optimization problem, including velocity and acceleration constraints of the drone. So we are able to avoid obstacles, maintaining a safe distance between the drones, and even do a fast replanning, tackling the disturbances and unforeseen events once we are tracking the trajectories. Even we can consider this as a minimum energy problem, which is again our like within the task to save the battery time or to be able to do as much of the job within the limited flying time of batteries. Yeah, so this is the last slide of my presentation before I pass the word to my colleagues. So I want to tell you that we have a lot of different projects in different domains. We have a project on using or doing inspection using a radiation sensor by multiple drones. So it's again a kind of inspection where the task may be to measure the radiation map of the environment, or even to localize and track a source of radiation in the case of an accident or terroristic attack or whatever. So we are again using the advantage of multiple cooperating drones, where these drones can carry small detectors, radiation detectors. And since they are agile and they can fly closer to the potential source of radiation, they can achieve better performance than using large detectors. We have been using even this technique on a satellite. So a colleague of mine from my team or even 2 colleagues, they are designing some software from satellite missions. So they have even now a satellite on orbit with their detector and with their software. Yes, and we have multiple others, industrial projects on inspection of different infrastructure, like stadiums, large halls, so not only historical buildings. But I have to say that most of the techniques are complementary. So thank you for attention, and sorry for being so long, but hopefully I'm on time. So we have some time for questions or discussion. So feel free to ask me if you want. I'm not sure if the audio is working here, because I could see that somebody switched off mic, but so if there is no more, so you can write it to chat if somebody wants to say something and we cannot understand. No, but now
there was a question in the chat, but I think it's more suitable to the second presentation, which we will have, so I will postpone.
So you will answer this question, okay? So if there are no questions, thank you again for your attention, and my colleagues will prepare their presentation. Right.
Right now, thank you everyone.
So so it's 10.
Yeah. We will start with another presentation at 11. So if there are no questions, thank you, Martin, for the presentation, and we will have a small coffee break, and then we'll be back at 11. Okay, so let's start with this session presentation block. Welcome everyone. I am Pavel Petráček. I'm a PhD student at the Multi-Robot Systems Group at the Faculty of Electrical Engineering in Prague. And together with my colleague Vít Krátký, we will now present, finally, after the long introduction from Martin, the Dronument project itself, the challenges of it, the motivations, the tasks we tackle in our research and which we tackle in our technical solutions. And I will show you the beginnings of the projects, the preliminary results, and up to date formations of multi-robots in indoor churches. You will see a lot of video shots, a lot of photographs. So I suggest to look at the presentation to see nice videos, nice pictures. So the motivation for documenting of historical churches, I think, is clear kinda to everyone, because if you have a really tall, large building which you want to document in high areas, you cannot reach there without building some scaffolding installations, like you can see on the left picture. And you have basically no solutions how to obtain the data in high areas of such buildings. What can you do is that you take modern technology in the form of aerial vehicles, aerial robots, and you can fly there and take pictures remotely or autonomously. Or what is done in industry today is that you have those drones, those commercial drones. You just buy them, you start them, you fly there remotely, manually, you take the pictures, and that's all. But this solution has similar or a lot of drawbacks. One of them is that commercial drones support some level of collision avoidance, for example, but if the density of obstacles is high, or these obstacles are small, like some thin ropes hanging from the ceiling of the historical churches, you won't see them. The quality of photographs is usually not really good for restoration purposes and for the end users from the field of restoration and documentation, but from which of many of you are, I believe. And also commercial drones are not modular, meaning that you cannot swap sensors. For example, if you want to take photos in the visible spectrum and then you want to take photo in ultraviolet or different spectrums, you cannot change it seamlessly. So that's why we also developed a custom or application-tailored solution for hardware, which is modular, which respects our constraints of flying in narrow corridors, narrow passages, and of course in atrocious or in high areas of historical buildings with atrocious lighting conditions. You can see the platform on the figure here. I will be talking for a short while in a few slides later about the hardware itself, about the parameters of the camera and of the data we can capture, etc., etc. To start, I will start with how the project started. This is, I think, 4 years old video, and you can see video shots from the St. Nicholas Church on the Old Town Square in Prague. Not this one, of course, the video before. And basically, this is before the project started, and we wanted to verify whether aerial drones, whether fleets of aerial vehicles could benefit the restoration purposes and the field of documentation, if we could acquire data which could be useful, and if the project actually makes sense. And we quickly, after one flight, decided that there's much potential and much space for research in this field. So that's how the project started. And now we are flying with multiple vehicles which are fully autonomous, meaning they will start on a press of a button. They will fly to the remote locations, take the pictures, come back, present the pictures, and that's the end of mission. But the technical process is pretty wide, and I will guide you through it step by step. I want to now start with the technical challenges of the documentation, which are or might be quite obvious, but it's good to highlight them. I think the first thing is that the churches, mostly the older one, Gothic churches and cathedrals, etc., and the older ones have atrocious lighting conditions, mostly in the high areas because you don't need light there. And that's why you have to carry lights on board your drones. You can have light on the single drone if you are flying with a single UAV. Sorry for the non-roboticist. I will be maybe like seamlessly transforming words from UAV, which is also drone, which is multi-rotor vehicle. It's the same. No, I don't mean any changes. It's the same meaning. And in those remote locations, you don't have light, so you have to carry it basically. If you have formations, one drone or multiple other drones apart from your main drone can carry the light and illuminate the scene. We will be talking about this later. My colleague after me will present some illumination techniques which can be applied to these formations and our approach to plan the trajectories for the drones such that the scene is illuminated in the best way possible. Of course, there is high density of obstacles. In the right picture, you can see the unit in the Château in Kroměříž, of which the hall you can see is in the UNESCO font. And though those environments are complex, meaning that there are the chandeliers with the hanging ropes and etc. So there's extreme pressure on the robustness of the system and on the safety. There are also arcs which are hard to detect, or maybe not hard, but the arcs are complicated because they are usually out of the field of view of your sensors. So we had to prepare for this. Of course, many of the historical churches are in nature symmetrical. So symmetricity is, for example, big technical issue or problem to solve in your localization and mapping algorithms. Because if your environment is symmetric, it's hard to distinguish motion, for example, in the onboard data. So this is also a problem. Huge problems might be if they are not solved. For example, dust conditions. Many historical buildings, of course, have not been touched by some cleaning guys for years, centuries. So the dust is settling there, and the UAV, of course, if you've ever seen UAV, you know that the whirling dust below the drone and above the drone as well is quite fast. There's a lot of air going around, so the aerodynamic influence of the UAV influences the environment, and the environment gives back the dust, and you have to filter this out in your data. It might be problem for your photo capturing devices and many other issues. And of course, when we are using drones, we try to push them as far as possible. So we even may fly into those remote locations where you can see in the left video, where we fly above the ceiling and basically below another ceiling. So we didn't know what's in there, and there was a lot of dust, and we aborted the mission in the end. And as I mentioned a bit, is that we apply huge pressure on robustness and safety of the system. And one of the low-level controls for this is, for example, collision prevention system, which does not allow even the safely pre-planned trajectories, which are visually controlled by the human operator, which are controlled by the computer and by the algorithms. Below that, during the flight, there's another collision prevention system which does not allow any UAV to fly closer than some pre-specified distance to obstacles. So this is, for example, if you have a map of the environment and somehow you don't have in the map some rope because you have not seen him from the ground, and your onboard sensors detect it. This is the mechanism which will make your system safe. And from the robotics point of view, huge issue is, or huge challenge, for example, is localization and precise mapping in indoor churches. I talked about the symmetricity. It's one issue in this. Another issue is how to use the map of the environment which we have for each object. I will talk about this a few slides later. So this is just some visualization of our formation of two drones flying and localizing mapping in a church. The mission itself, the documentation task, consists of several steps. I will be talking about 8 steps. I will go step by step, and I will try to showcase how the entire documentation process works, from the preliminary preparations up to the mission and to the processing of the data and presentation of the data itself, which we capture in the high areas of the historical buildings. So the entire process starts with the information that we have site. We have a historical church which we want to document, and we as a robotic can go there and we take a map of the church. This is important for two cases. The first one is that we use the map to localize our drones, our UAVs in the map during the mission. We use this map to pre-plan the trajectories of the UAVs. We also use this map to specify the mission, the objects of documentation interest. So the end users actually can select documentation points in the map, and our automatic annotator will translate their needs to our robotic solution, basically. And the second case of usage of such a map is that because we have the map, we can provide this map to to the people which are taking care of the church, which is often welcomed in the community. And this way, every basically church we fly in, we also make publicly available if the church administrators allow us to do. So you can see on those pictures some scans of some churches. I think this church is from Olomouc. The left one on this figure is from Prostějov, and the right one is from Cholina. All of them are in the Moravian region of the Czech Republic. And on those figures, you can see on the right side, for example, our robotic our representation of the map, so-called voxel grid, which we use in our robotic application to efficiently work with the map. So here you can see the process from being at the site, having the scan of the environment, and having it translated for the robot. Once we have the map, we can create a 3D model. You can see some snapshot from the 3D model in the figure. And we give this model to the end users, to the restorers, historians, and other experts, and they may specify in our annotation to the documentation point of interest. So it might be whatever. Basically, it might be paintings, some statues, altars, doesn't matter. They can specify the parameters of these sensors. So I don't know, for example, I want a detail of this scratch on the wall, and I want it to be highlighted from the side with the raking light. And our annotation tool creates a set of positions for the drone where it should take the photograph for the camera drone. And we have this set of position, and this is probably the first place where some research goes into. The problem is how to most efficiently, with respect to some criterion, plan this multi-goal planning task, where you have the set of drone position or the documentation points of interest. In this figure, the red dots are example of such objects of interest, and the blue dots are the positions of the camera drone, and the red trajectory is the planned multi-goal trajectory of the UAV, which in this case probably have been planned with respect to minimum time or minimum energy of the flight. In our automatic tool, we can, if we have a huge amount of points, like for example, tens or hundreds of points which we want to scan, our tool divides this multi-goal planning problem divides this set of goals to subsets which are then like used for different flights of the UAVs. This is because the UAVs, of course, have limited battery capacity, so they can fly for. That depends, but let's say you have a drone which can fly 10 minutes, but you have a huge amount of points which cannot be photographed in 10 minutes. So you have, for example, 30 minutes of flight. You need 30 minutes of flight time, but the multi-goal path planner and trajectory planner divides this problem to 3 trajectories, and you fly with you fly your mission 3 times. Another task in the entire mission pipeline is that before the mission itself, before the documentation task itself, we want to simulate the mission. So we have the trajectories, we have the model, and we use a realistic robotic simulator called Gazebo. And in this, we can basically run the mission as in the real world, and we verify, and we try to verify it, and we try to find all the possible drawbacks. The people which are at the site may see what will be happening in the real world afterwards, and this is extremely useful to debug basically the mission, to debug your system, to find find drawbacks and to see how the system will behave in the real world. After that, it's the mission itself. So here you can see example. We'll start the video. You can see example of one of our latest flights in church in Prostějov, Czech Republic. We have prepared a mission plan, which is basically the black trajectory of the drone in the right video. That's the visualization of the drone. You can see the map, which is the colored point cloud, and in that you can see black dots. Those are the data from the main sensor of the robot. I will be talking about what is the sensor later. And in the left image, you can of course see how the drone behaves, what it does, how it tracks the trajectory. You can see that it stops for a while. That's the moment where it's taking photographs, and then it flies to some different position. That's where the transition between the 2 points on the trajectory happen. So we do this. We have the points specified, and we stop in every point for a few seconds to take pictures. We take pictures at the different exposures because the drone is shaking and the stabilization is good, but it's not perfect. We take several pictures, so it doesn't happen that one of the spots is missed by the camera, and we don't have quality data from that remote position. And after the mission itself, after it ends, we verify the data at the site. So we see the data, and we see if they are fine for the restoration purposes, for the end users. The end users are usually there with us, so we have direct feedback. But in the future, it doesn't have to be. In the future, if the system is finished, there does not have to be anyone except one person who will launch the mission and go home, basically. So here you can see few shots from the UAV itself. You can see some artifacts from the churches. So those are onboard photographs. And after we verify we have the data from the site, the mission is complete, we can go home. We can run some data processing, we can create some orthomaps, for example. That depends on the objects and on the purpose of the documentation task, what the end users want. And here you can see, for example, some vitri. How is it in English? I think it's vitri. So this stained glass window. And you can see the tile of the top. This is in 12 meters above the ground, I think. So on the right figure, you can see how the photos look from the ground. You can see there's a chandelier hanging in front of the window. And with the drone, we flew behind it, so we don't have it there. And we have the photos captured from better angle than from the ground, of course. And this is extremely important in the process. Those photographs, for example, were used to state or to assess the state of those stained glass before restoration. And the last task in the documentation process is that we present the data online for either publicly or privately for the end user. So the data go from the roboticists, from us, to people who work with them, and they of course want to localize themselves in the church. That's what you can see here, and they want to see the pictures associated with the spatial representation of the church. So we developed a framework for online browsing of those models and visualizing of those photographs, as well as we can place text there to comment those objects and etc. I can show you this online viewer right now. You can actually browse it on yourself. It's this 3D model viewer on our website. I will write it to the chat quickly. And you can access this site on your own. Beware that if you are on a mobile cell data, it might download a lot, so don't do that. For example, this link I will click on right now, this interior, is half a gigabyte. So I don't recommend it doing it on mobile phone, but it works on mobile phones as well. And a church will open for you with some default view, and using arrows on your computer, you can navigate through the model. You can see that we are in church. This one is St. Maurice Church in Olomouc, again in the Czech Republic. You can see some numbers here. So if I click on some number, for example, number 3, you can see that this is a comment for high altar of the church. You can see the altar, the 3D model of the altar here. You can see some text about it, some description with some bibliography as well, which is quite nice. And you have some pictures here. You can click on them, and you will get high resolution picture, which will download for you, which can be taken from the air as well as from the ground. Those are this one is, for example, from the drone. So check it out. It's quite cool, and we are still tuning this. We also have high quality stained glass windows here. So those were also taken by the drone. There's one missing frame, but we don't finish it yet. But there are basically the windows or the textures are mapped on the model, and those were taken by the UAV itself. And there is more objects if you want to see. There's, for example, this facade of Chapter Plumlov, again in the Moravian region of the Czech Republic, so we can see it as well. Let's go back to the presentation itself. So this was the pipeline of the mission. Basically, step by step, showed you how the procedure of the documentation task goes. And then as a roboticist, I will focus now on the robotic part. Later on, we will have presentations of our colleague from the restorer's field of view, and he will talk more about what our data help to accomplish, what is the current state, and what maybe we will even talk about drawbacks. I don't know, probably he will, and that's non-roboticist point of view. My point of view will be coming from a roboticist. So there are a few existing solutions which could tackle this entire project, but they have huge drawbacks in our opinion. The most cheap or the cheapest one and the safest solution is to go with some commercial drone. For example, DJI Mavic. You can buy this for 1,000 euros. And with this, you have some collision prevention, so it won't let you fly into obstacles. You can manually fly just below the ceiling and take photos. But the issue is the photos do not have significant quality. This is good for initial assessment of the object or fast picture taking in the remote areas. But it's not good for if you want the outputs to have high quality. Another solution might be Skydio X2. This is a company which have a great potential in the inspection tasks. They have nice video. You can check it out on YouTube. They perform mapping and inspection with Rgb camera, but again, the quality of data is not sufficient for restoration purposes, and also the quality of the maps built from the drone are not so precise, because as they rely on the Rgb camera only, they don't have such precision as we do with a 3D LiDAR. I will be talking again about this a few slides later. In the last year, we published a paper with our preliminary results. Basically, this paper summarized everything of what I've been talking so far. It summarized the challenges of this project. It summarized it showed the first objects we flew in, and it also presented, or it tackled the problem of localizing and mapping of our UAVs inside interiors without access to GPS, to global navigation systems. So in our preliminary works, we tackled this using a two-dimensional LiDAR scanner on board our vehicle, and we basically localized in the scan map using just a planar scanner and two point-based distance measurement sensors, one up and second one down oriented. And this way we were able to localize in the church, but we found out that the reliability was not sufficient for this task with high pressure on robustness. And we also, at the end of this preliminary task, there were new sensoric solutions coming to the field. So we went from two-dimensional LiDARs to three-dimensional, and that allowed us to do basically magic. That brought us to the future. This is, for example, the video of the preliminary work from the paper. We got quite nice localization error, but in my opinion, the reliability of this approach was not sufficient. And that paper also specified how the mission should look. I've been talking about the 8 steps. And from the mission itself, it specified that we should be able to either run the mission fully manually, meaning that the data are captured on board the UAVs, but the operator is controlling this mission remotely. This approach is neither the fastest one, it's neither the most robust one, and is how we did it in the past, but we are in the future now. So we may run the system semi-autonomous or autonomous fully. The semi-autonomy means that the UAV is flying using its onboard sensors, but the operator can set references where the UAV shall fly. It may set the parameters of the camera. It may set the parameters of the illumination, etc. during the mission. This might be usable in some cases, but what we tackle is full autonomy, which means that we press the buttons and the UAVs take off. They fly their mission as it was planned. They of course check their subsystems on board if everything is okay. There are some diagnostics going on. There are some procedures which allow us to abort the mission in case of some failure. There are always in the loop are some skilled flight pilots which with a switch of a button can go to the manual mode and land. But this year, for example, this was not needed at all. We flew in several historical objects and we haven't touched the manual mode at all. So the system is now in quite good state, and with a switch of a button, it flies the mission, takes a photo, and comes back and presents us the data. The advantages of the autonomous mission are mostly that it improves a lot the safety and robustness of the system, because if you are flying in centimeters right below the ceiling manually, you don't know your perception of height of the UAV is very bad with your own eyes from below 20 meters. And if you have onboard sensors, you can basically fly there with no issues, because you are measuring your distances. You can see how far you are from every object around you, and you can plan your motion accordingly. It's also much more efficient because the drone can stay at one place, it can hover and take the pictures for the exact needed time for the photo capturing. If you would fly manually, you would probably have issues with hovering at all right before the object, so your photos would be blurry and the data would not have the sufficient quality. And of course, the automatic mission can also improve the quality of the data. It allows repeatability, which is which is beneficial from 2 points of view. The first one is that you can do the same emission like in different lighting conditions, meaning you can fly there in the morning when you have the morning light, and then you can fly in the evening when you have the evening light, when the light is bad, and you can fly the exact same mission, and then you can compare the same data from different times. So this is one point of repeatability. Second one is that you can perform a mission, then you can swap a sensor, meaning that in the first mission you take the pictures with Rgb camera, then you swap your sensors and you have there, for example, infraviolet or ultraviolet, sensitive camera. You take the data in different spectrum and you compare this. This is useful because aerial drones have limited capacity on weight and on flight time. So this way you don't need all the sensors, which are usually quite heavy, on board at the same time. So you can just swap them and fly again the exact same mission. And I talked about that it allows you to fly in more complex environments. And also it's scalable to multi-robot formation. This will come handy after 10 slides, where we will be talking about formations. And you basically cannot fly formations manually because the human pilots are not synchronized and everything will break. You don't want to do that. And for this, you need autonomy. We developed custom built hardware platform. You can see it again on the pictures. We modeled it. That's the left picture in a CAD program, and then we build it. We have mechanical propel guards, which are useful for the last case where everything would fail. They would prevent from scratching the walls by the propellers. And you can see the camera there, which is stabilized on 2-axis gimbal right there. This is mirrorless Sony Alpha 6500 camera, which is basically commercial camera. You can buy it on your own. We feed the video from this camera to video transmissions on the ground. The operator and the mission planner and everyone who's on the ground basically see what the drone sees, what pictures the drone is taking right now. Above the main Sony stabilized camera, there's Rgb Depth Camera, which we use in a robotic solution in localization and mapping. And it's not quite clear seen, but at the most top platform of the UAV, there's a cylindrical shape, which is black and white, and that's a three-dimensional LiDAR, which measures distances up to 50 meters in all around you horizontally and in 90 degrees vertically. So you have quite a lot of this spatial measurements in real time. This sensor may run on 20 hertz, meaning 20 times per second. So the speed of your data is great, and this is used for mapping. This is used for localization. This is used for collision avoidance with obstacles. There's a question in the chat that what is the total drone weight? So on the right side, the drone weight is 8 kilograms. There are 2 batteries. Together they have 1.6 kilograms. The camera with the gimbal is another 1.2 kilograms, I think. And then there's an onboard computer, which is a commercial Intel NUC computer, which is running all the processing of the data. We communicate only, there was a question about communication. We communicate only via Wi-Fi, classic Wi-Fi. In the churches, it's not an issue. We don't fly long-range flights. Basically, we fly in continuous visibility. So this communication is not issue. We didn't design our system to not be robust towards latency of communication. So this is something we tackled as well. So if there's slight latency, we don't care, and even in the formations. So this is the hardware platform, but just to say another point is that we try to design it to minimize the dimensions, so we can fly in the most narrow passages of the churches, while it maximizes the payload capacity, meaning that we want heavy sensors there, we want them stabilized to have the best data. So the drone is is big. We don't have it here, unfortunately, but it's 80 centimeters wide, I think. So it's below 1 meter, and that's because the payload is quite heavy. But the data from it are worth it. This is probably the largest like difference towards commercial solutions, which offer some kind of autonomy, but the quality of data is not sufficient. You can see here the data which sees the 3D LiDAR, which I've been talking about, the topmost sensor on the UAV. So the red points are the spatial points which the drone sees during the flight. So this way we can localize and map ourselves in the environment. For example, even using the black map, which is the pre-scan map of the environment. I also talked about that we see on the monitor what the drone sees. So here is live video feed. Here is a picture of a live video feed from the camera itself. It's not clearly visible, but it's from the camera. And that's basically the pipeline again. Pipeline with now hardware as well, and the entire mission. We are capable of doing. I've shown you one video before. This is similar one. Again, we documented some object of interest, which in this case was some altar in a church in Olomouc. The drone now, I estimate, is in 15 meters. This church was like 20 meters high, so there was issues again with getting humans up there without building scaffolding. So there's again autonomous trajectory of our UAV, which goes point by point, takes photographs and lands. I will run this quite time, so for a while, so you have you can get some notion of how the mission looks. This is in real time. We fly kind of slow. We can limit, of course, the desired velocity. We could fly fast, but we don't want that. We want to maximize robustness. So we fly below half a meter per second. In here, I think it was 40 centimeters per second. But we hover most of the time because we are taking the pictures. And you can see the blue dot on the UAV. Maybe you can see it. And that's a diagnostics LED, for example, that checks the hardware, whether the hardware is okay and everything is running. If something would be slightly off, it would start blinking red or give us some warnings, and the operator could take over the mission and land, and the hardware should be repaired, and the mission might or might not be repeated. There's again a question in the chat about open source of our system. Yes, the system is open source, and you will find the open source code at this link, as well as on our web pages. And that was single drone missions. And we would like to talk more about formations of UAVs. This is motivation for you. This video shows two drones. One is carrying light, that is the one on the right side, and there is the main camera drone. And they communicate. The leader, the camera guy, flies using the propellant trajectory, as I've been showing before. It follows the trajectory, and the second one or positions itself online, like they are communicating. So the second one is positioning itself with respect to the camera guy, and in such way that the scene is illuminated from the pre-specified angle. So in this way, we could get more details of the scene. We could get light from a different angle, and this is quite useful for documentation. My colleague will now take over the presentation, and he will talk more about those illumination techniques. Some techniques which we already did and some techniques which we plan to do. And he will show you more on formations, formation control, trajectory tracking, and etc. So I pass my word to Vít Krátký, and thank you for listening my part.
So thank you, Pavel, for the introduction into the single UAV part of our system. And as was already said, I will now follow with the description of the techniques that were implemented by us, the more advanced documentation techniques that requires more than single drone. As you can probably imagine, most of the parts of the historical buildings are not sufficiently lit, so they require some additional lighting, since the exposure time of the camera, which is mounted on the UAV, is limited to reach desired sharpness, since the UAV, even if it is quite well stabilized, it's still not similar to the tripod standing at the ground. So there will be always at least a little motion of the camera, which results in the blurry image. As was already said, we can use light which is mounted on the same UAV which is carrying the camera, but this results in the direct lighting, which is not ideal in most of the documentation techniques. Since the light is a powerful tool, we will be dealing with the formations where one UAV is carrying the light and another UAV or more UAVs are carrying the lights that can be positioned at an arbitrary angle with respect to the camera. On the slide, you can see the same object captured by the camera at the similar position, but under different lighting. On the left, there is a direct lighting from the same direction as the camera axis, and on the right, it is the image which is taken under the so-called tracking light, which is positioned as close to the picture as possible, which results in completely different information which you can extract from these images. While on the left one, you have a great view on the colors. On the right one, you have the information about the three-dimensional structure of the image and some roughness on the painting. So the documentation techniques that we have implemented and tested in the churches are namely the three-point lighting, the raking light, the reflectance transformation imaging, and partially also the infrared and ultraviolet reflectography. All these methods requires more than a single UAV to be performed. So the first technique that we have implemented and tested is a three-point lighting method, which is mostly used in 3D computational graphics for the image rendering and also by the filmmakers. And it's used to make some three-dimensional structure look quite or closer to its actual appearance in the flat image. As the name suggests, it applies 3 lights. The main one, which provides most of the lighting and has usually the higher intensity. The highest intensity is the key light, which is usually positioned at 15 up to 45 degrees on one of the sides from the camera. And as I have said, it provides the main illumination of the object. The second light is the fill light, which is positioned on the opposite side from the camera. Then the key light. And this light is used for filling the overshadowed parts of the image that are caused by the key light. And the last light is the backlight, which is used, which is positioned in the back from the object, so on the opposite side than the camera. And its purpose is to divide the object from the background, or separate, let's say, visually. This technique we have implemented and described in the manuscript, which was published in 2017. And our approach was based on the leader-follower scheme, which means that there was a leader UAV, which carries the camera, and it has pre-specified the path which it should follow, and also the targets or the objects of interest that should be captured during the flight. And while this UAV is following the trajectory, which is generated by proposed trajectory generation system, it communicates with the other UAVs that carries the light, and it sends the trajectory, which it will follow in the next seconds, to the followers carrying the lights. And based on this trajectory and on the position of the currently scanned object, it generates its own trajectory to reach the desired lighting, which was specified prior to mission. There is a video of this approach. It is from the simulation. We have not been flying with 3 drones in the church so far, since you can see that here only 2 drones are used. Although it's the 3 points lighting method, in general, you can use arbitrary number of these drones, and it depends on what you want to achieve. So, for example, if you are filming or scanning some paintings on the wall, naturally it doesn't make sense to have a backlight, since you cannot even position it in the desired place. We have applied this method, which is, in this case, limited to the use of a single UAV carrying the key light in the church of St. Anne and St. Jacob the Great in Stará Voda. And here, the 2 UAVs, which I hope can be seen in the image. Here is the leader with the camera, and here is the UAV carrying the light. And they are scanning a painting, which I think it's clear, but it's this one. So they sequentially visit 16 positions and take a picture here with the additional lighting provided by another UAV. in most of the cases, we use only a single UAV with a key light, since if the objects are flats, there's no need for the fill light, and naturally there's less. There are lower requirements for the space in which the formation is deployed. Okay, so this is the work which has been already shown there, and this was aimed. It's a recent work, so it's kind of based on our previous works, but it was primarily proposed for the aerial filming and for the monitoring of the worker in the inspection tasks. But we have tested it also for the inspection tasks itself. And I think that I won't be describing the technical details here, but the advantage of this approach is that it enables to generate longer trajectories, so we can avoid like bigger or more large obstacles that are detected during the flight, and that we are also able to fly in more constrained environments, as you can see now in the video. So far, we have tested it only in the external environments. So here you can see a video where the 3 drones are following a person. And we plan to modify this and test it in the inspection tasks in churches as well. This work has been done with the cooperation with University of Sevilla. So another method which I will be talking about is the reflectance transformation imaging, which is an image-based rendering method that enables interactive displaying of objects under varying lighting conditions, as you can see in the video. And therefore, it's often used for surface inspection. As far as I know, also in cultural heritage applications. The necessary input to this method is the set of N images that are captured by a static camera, but each one under illumination from a different but no direction. And based on these inputs, the so-called Polynomial Texture Map is produced, which is a representation of the image where each pixel or its intensity is not represented by a static number, as we are used to in, for example, RGB image, but it's represented by a function of the lighting vector. So based on the set of images and the intensities of each pixel measured for particular lighting directions, the coefficients of the functions for particular pixels are computed, and then you can display an image under, let's say, almost arbitrary lighting conditions. So as you can see in the video, then you can move the light around the object, and it's displaying under the required illumination. The common techniques that are used by historians and restorers nowadays is an Rti Dome, which is a device that consists of tens or hundreds of light-emitting diodes that are placed on the inner part of some hemisphere. And the scanned object is placed under this dome, and the light-emitting diodes are sequentially lit while the camera mounted on the top of the hemisphere is taking the images. Since this device is relatively small and you can mount the light-emitting diodes wherever you want, you can exactly measure where the lighting diode is mounted and also the direction towards the object. But as you can imagine, this device is, its usage is rather limited to the laboratory, and it's not so practical in the field. The second method, which is often used for the image acquisition process in the reflectance transformation imaging, is the so-called highlight reflectance transformation imaging. And this method enables to position the light manually to unknown positions that has to be in the same distance from the scanned object to reach similar intensity of the light. And the images are taken by the camera, which is mounted on the tripod, and the positions of the light or the directions are then estimated from these high reflective balls, where you can see the from which direction the light comes from. So there is an available software for this estimation and also for viewing the final polynomial texture map. As you can imagine, this method is more suitable for its usage in the field, but the remaining problem is that you still need the direct access to the documented object, which is not always possible. Therefore, we have proposed another approach, which is based on a team of UAVs. We call it distant autonomous reflectance transformation imaging. And in this method, the camera is carried by one UAV, which is hovering in front of the scanned object. And the second UAV carrying the light is flying around the object at a certain distance, which is constant, and is visiting a predefined positions where the light should be placed. During this process, the UAVs are communicating with each other. So the UAV carrying the light sends an information that it's already in the place, and the UAV carrying camera is taking a picture. Once the picture is taken, the UAV flight follows to the next position. So here is the set of images that you've already seen, and the resulting polynomial texture map, which was already shown. And this method we have deployed during the experiment in Church of St. Mary Magdalene in Chlumín, where we have scanned a pulpit, which is accessible, but we chosen this object since we want to compare the results with the highlight reflectance transformation imaging method. So we need to place a reflective ball there. So the positions of light were only 12, since there was no much space for the motion of the UAV. There is a comparison with the HRTI method, which is on the right, and our method, which is on the left. The images are the same since the camera was positioned at the same place, but the difference is in the estimation of the lighting vectors. While on the right, they were estimated from the reflections on the ball. On the left, they were estimated based on the localization system of the UAV, which was carrying the light. There are several issues that need to be solved to make this method applicable. The first one is that for the common RTI method, you need your camera to be static, which is not the case for the camera mounted on the UAV. But this can be overcome by some image registration method. But the second problem is that the localization of the drone does not have to be so precise so that it produces high quality results. The issue with light is that in difference to the camera image, we don't know a method how to, let's say, register the light and align it to some place. So we really need to rely only on our localization system. To prove that the precision is sufficient, we have compared the results from the modeled localization error, which is achieved generally by our system, with the ground truth localization in the simulation, and the results you can see in the image, where an image on the left is the result or the normal map, which results from the localization with the precision similar to our system, and the image in the middle is the ground truth obtained with the ground truth localization. Since, at least for me, the images are the same, the difference between them is shown on the right, where you can see that there is a certain distance, but we have not found any metric which can say that this is not good enough. And according to our discussion with some experts which use this method, they are not so interested in the precise normals of the surface, but more in the difference, since they want to find some stucco which is not in the right position, and the difference is very low, so that you can, for example, see it only from one angle and not from the, say, 2 degrees, not from the angle different by 2 degrees. During the development of this method, we have found that following some pattern, which is kind of regular, is not optimal. Since if you follow the pattern on the left and make a camera image with lights positioned at the right dots, you can miss some parts which are interesting when the shape of the object or its surface is kind of regular. So if there are regular lines in the same direction, in which you follow the positions of the light, you will miss some information. Therefore, we have started to work on another approach, which comes from the idea that if we have a general object, there is no need to visit precise positions from which the light should come, since they will not be optimal for the general object, but they are specific for particular objects. Therefore, we have said that it will be sufficient to cover the area, and for this we have defined some areas that are located on the surface of the sphere, and define a problem so that we would like to visit surrounding of each position. We would like to visit each area which is a surrounding of certain point that are equally distributed or approximately equally distributed around the surface of the sphere. This method we have applied in the church in Stará Voda, where you can again see the UAV with camera, which has a blue LED on its back, and then the moving UAV carrying the light, which is following the trajectory generated with the newer method, which has not been published yet. You can also see that the UAV is no more stopping at each position. That's because the exposure times are really low, and the motion during the exposure time of the UAV is negligible. And since we do not want to visit a precise position, it doesn't make sense to stop here. And the UAV can capture the image. The precise time is not defined, so it can capture the image almost at any place during the trajectory. Okay. Another direction of our research, let's say in this project, is the interaction with the environment, which is needed for two problems. The first one, or two techniques. The first one is the raking light, which requires to position the light near, really as close to the wall as possible. But as you can imagine, it's not so safe to fly, let's say, 10 centimeters away from the wall with your propellers. So the colleague of us have designed a system or device which can fly to the wall and touch the wall with this device, where are mounted the force sensors, and then while it's touching the wall, it's controlled also based on the measurements from these sensors. This enables not only to position the light as close as possible to the wall, but since the UAV is also more static with respect to the wall than if it will be only hovering without touching the wall, it enables also to mount some temporary sensors that actually exist. These are some small sensors that can be mounted on the wall just by pushing them against the wall. And then they measure, for example, the humidity or the temperature at different places in the church or other structure. And after several days, or weeks, they fell off and their function is quit. The last lighting technique which we have implemented, or rather tested in this case, is the infrared and ultraviolet reflectography. The main issue of these methods is that they require the exposure time of tens of seconds. So it's not feasible to make an image by the UAV, since it will be always blurry. But from the discussions with the restorers, we find out that it can be handy to use the UAVs as a carriers of the infrared or ultraviolet light sources, since they can place the light near the objects that should be lit, and so significantly less powerful sources are needed with respect to the lighting sources that are placed at the ground and illuminates an object which is, let's say, 20 meters far away from the source. Okay, so this brings me to the end of our presentation. So let me only shortly introduce our planned future work. The first part, which I don't know how surprising it is, but the first part is that we want to improve all parts that are already implemented, since there is always room for improvement. And every time we test it in some object or deploy it for the documentation, we find some features that can be useful for the next time or for the general use. And the second thing which we would like to aim at is that we want to make the system as, let's say, user-friendly as possible, so that it can be used by people that want to gather the data, and they don't need an expert in robotics or in some technical field to apply the system. So I think that's all from us. So are there any questions regarding our simulation, our presentation?
There was the question, like, did the first presentation slot, and I hope I answered it during my presentation. Basically, it was about communication. So I talked about it's Wi-Fi and the drones can communicate via Wi-Fi. And how do you handle safety? Do you have a single kill switch or other methods? Yeah, so this is quite large topic. So I will tell that we have subsystems which check and monitor the health of the software running on board. They check whether the data are coming, and we also have hardware stuff which checks the sensors if the data are coming, like on the physical layer. We have mechanisms to land autonomously, of course, to abort the mission and go back. And we also have the human operator in the feedback loop, which can, with a switch of a button, remotely overtake the control and land. So those are the two main procedures. It depends on the reaction, depends on the state of the failure. What is the failure? We have, for example, motor redundancy. We have eight rotors. So if one of our rotors fails, we are still able to land. This did not happen to me yet in my short career, but it may happen because it's still hardware. So one motor may break, and in this way we can land safely. So this would be example. A motor failure would be example of manual overtaking of the UAV, for example. But the single kill switch is there on the autonomy level. The autonomy handles the mission abortion. For example, if one UAV during the mission somehow fails, or for example, its mapping fails, or its indoor localization fails, or something, it will send these diagnostics to the mission operator. He can abort the mission, or the UAVs can abort the mission on their own. So hopefully that answered at least. Yes, that's right. Again, the testing we do, thorough testing in churches and in simulation, are towards maximizing the robustness and the safety. Because we have for example, we have the pre-planned trajectories. So during the mission, we check whether the trajectory is tracked in a correct way. So if it wasn't tracked in correct way, we would abort the mission as well, because something is of course wrong and the UAVs do not perform the planned mission, and something is wrong and you don't want to fly because it might be dangerous. So there are several layers of robustness, safety. Is there any other question from the audiences? Virtual, physical. If you had some close calls in the churches that you can comment on. In the early phases, we were flying mostly we call them testing churches. Like there are some objects which are already destroyed from the inside, so you cannot destroy anything else there. And those are mostly from the Soviet era, and during our preliminary flights, we had even some crashes before we solved some technical issues with localization and other stuff. So yes, it might happen, but it hasn't happened for several years, only in the beginnings. But that's probably connected with our experience with UAVs. Our research, as during the first presentation Martin Saska held, he discussed that all of our projects are somehow connected, and the autonomy which we open sourced is used in all of those projects, and it's tested in many different environments, in subterrane environments, in churches, in outdoors, on the field, close to the power lines, and etc. So we are not testing it only in the churches, but everywhere.
Another question is for the multi-drone lighting case, how do the drones communicate? So I'm not sure which one is meant by this, since they differs a little bit. For example, the reflectance transformation imaging and the 3-point lighting method. But in general, they communicate its current position, which is used for mutual collision avoidance. Then they plant trajectories, which are also avoided, and the leader's trajectory is also used for the computation of the trajectories of particular followers. And last thing that they communicate with each other is a diagnostic message, which says whether the UAV is ready and is proceeding in the mission as it should, so that the others knows that it makes sense to follow the mission. Because, for example, if you are photographing some structure and your leader with camera fails, it doesn't make sense to follow the trajectories with UAVs carrying the lights, since you have no data then. And if the questions aimed at the reflectance transformation imaging, then there is additional communication regarding being in the position prepared for the photo capturing, and that the photo was captured so the UAV with flight can move to another position.
I can add to this that during the mission, the robots may stream the data to the ground station, which might be some notebook which has the mission operator, or which is the mission operator using. And in there, he can visualize the trajectories, the maps, the robot data, and this is quite useful also to assess how the mission is going, whether it's going fine or something is wrong. And this goes also through basic Wi-Fi communication. Basically, in the churches, the entire bandwidth of the radio Wi-Fi is for us, because there's no Wi-Fi, so we can use it freely. Okay, any other questions? If not, thank you for listening to our presentation. Thank you, Ed, for assisting me. How would we scale to much larger structures such as factories or power plants? And yeah, meaning like with a number of drones, scalability.
Yeah, so it depends on which level it should be done. But one option is that, as was already described, the potential user of this system defines which object should be scanned and captured. And then our system plans a set of paths that are connecting all these positions. And the reason for the set is, if you remember, is that you have a limited flight time, and if you have hundreds or thousands of these positions, they cannot be visited during a single flight. So if we will have multiple drone teams, we can assign these particular plans to particular UAVs, and then this problem will be solved. If the question aims on some replacement and cooperation during the mission between several teams, then we have not tackled this issue yet.
If I may, I will add that in the churches we fly slowly because, again, the safety. But if you would inspect factories or power plants or the power lines, then you can increase this speed, particularly in the parts of the mission where we are not taking data, which is mostly take off and going to the first documentation spot. This might be tens of meters, maybe even hundreds, and this way you can fly fast. Those UAVs which we are using can fly something up to something like 6 meters per second. So that's quite fast, and this could increase the scalability to larger buildings, and larger environments as well. So the missions of taking photographs could be longer. Thank you for the interesting questions as well. Again, last call for questions. If not, thank you everyone for listening. Now there will be a lunch break for 1 hour, and after that we will stream a live demo, really a demo of our system in a gym in Prague, where we will deploy the main drone you are seeing on the video, like in a short demo mission. So we will meet in 1:30 p.m. in 1 hour. So see you then.
For the offline participants, you can meet in front of this lecture hall at the same time. I think, whether we can ask Tanya that she will lead you to the gym. Thanks.
We are in the gym at our university campus in Prague, at the Charles Square, and we will be doing the live demo of the Dronument system. You can see the drone here on the ground, together with the three-dimensional laser scanner. We will show you quickly the procedure of the entire mission. We will show you how we scan the environment. We will show you how it looks, how the data look for the drone, and then we will give the map to the drone, and he will scan one of the artifacts in this gym, which is the very, very old basketball rink. So for the demonstration of this system, this should be enough. It will be one drone only because the space is very limited and there are people inside. So to increase safety, we will be flying with just one single drone. We will share you now screen of our software, and we will show you how it looks. We use this commercial three-dimensional scanner. It's very easy to use. Just press the button, it will scan. Depending on the set parameters, it takes from 3 minutes to 6 minutes per one scan. The parameters are the granularity of points and the color. Basically, right now, we are doing the quickest scan possible, which is 3 minutes, which is without colors. Is it faster? 1 minute 20.
No resolution, 1 minute 10.
Okay, so the quickest scan is 1 minute 10. And the data we get from the scan look something like this. Sorry for the quality right now. Could you... Yeah. Yeah, this is fine, I think. So we have actually pre-scanned this area before. This is just to showcase. We've done 6 different scans. We registered those scans together, and we have one model which we will pass to the drone. Oh, like this. So here you can see we are in a cubic-like environment with a gym. We will take this point cloud and we will now give it to drone, and we will do the mission. So can you please share the screen now?
Our software for defining the positions of the camera from which the UAV should make the desired images. You can see that we can position the camera, and the software views also the field of view of our camera, which can be set, and now it's set exactly to correspond with the model of the camera which is mounted on our UAV. And by simple clicking and saving the positions, we can generate some set of the positions that should be captured. After defining these positions, we can save these positions to file and then proceed to the next step, which is planning the path which connects all these positions. So now you can see again the model of the environment. And now already with the path connecting the positions that we have chosen yesterday. And now it is the phase of verifying the generated plan, which will be now shown to the operator so that he knows what the drone should do. And then the UAV will follow this plan during the mission and capture the desired images.
Okay, so we now visually corrected that the mission plan is fine, and we may proceed to perform the data acquisition. Okay, so we now visually corrected that the mission plan is fine, and we may proceed to perform the data acquisition. We'll plug the battery in. Check. Close. So right now we plugged in the drone. In the video, actually, you can see the three-dimensional LiDAR rotating around its axis. It's the red light, which is blinking in the topmost sensor. Maybe it's not visible. When you zoom in, you can see the LiDAR rotating. We will now run the mission and we'll take off. So the virtuals. So we now started the mission. We have here in our. It's really hard. Yes, thank you. So here we verified that our drone knows where in the gym it is. It loaded the scan of the environment, which is this gym, it found itself inside, and there's a red line, which is the planned trajectory of the mission, which we visually again corrected that it's the correct plan we want to do. We also have we have display which shows us the live video feed from the drone, so we will see what the drone sees and what photographs it captures in real time. And we will now just press the button and the drone will follow the trajectory. Now when the mission is off, we will lock the drone so the motors won't rotate. We may take the data out of the drone, inspect it or take out the SD card, check the data, inspect them, see whether we have to do it again. And basically that's all. If there would be a second drone, they would be right next to each other. Both would take off at the same time, and then as the trajectory, the same one would be followed the lighting drone, which is this one. Sorry, Mityo, we have one battery, I could show the light. This drone would position itself with respect to this drone, and with respect, it would change the heading with respect to the documented object. The light on this drone, we have this like testing light drone. So we have here our lighting drone. It's a research platform. It has a controllable light. So for example, if we want to change the pitch orientation of this light, we can do it from software. And basically that's it. This drone is quite lighter than the large one because it doesn't carry the camera, but it also has the three-dimensional LiDAR to localize itself. It has other sensors like this depth camera, which is also RGB, and a computer, which is here too. Both of them have Intel Mac computers, which run all the processing. This computer communicates with an autopilot. Autopilot is hidden inside. I cannot show it. We use, here it is visible. We use the Pixel stack, which is open source autopilot. Basically, that's all. This drone is quite simple, much more simpler than the large one. Now you see the screen of my computer, and I can check the photos we took right now. So, as we were documenting the basketball ring, you can see some photos from this flight. We haven't set any parameters of the camera, so we had some random exposures and focal length and aperture. So, what the focal length was. The video, I'm streaming the video from me, so. So this is all we can show right now, because we don't have more spaces to fly in at our university campus. When we want to test something, we have to go outside. Basically, we prefer to go to some churches. As I mentioned, we have some testing churches which are destroyed, so we may test there, and we usually test there the more complex stuff which was not tested in any other of our projects, which in this project, it's many features, mostly the multi-robotic stuff, because that's quite unique to documentation and inspection tasks. I will now stop sharing my screen because you've seen the photographs, and you've seen at the beginning, you've seen the video is now. So you've seen the laser scanner, the entire procedure, you've seen the flight, you've seen how the data can look. We could make a 3D model out of the scan of the environment. We could make it with colors, without colors. We could, if we were in a church, we could make the 3D model and then pass it to the administrator of the place. And we would pack the things into our box and leave. The entire mission, the autonomous mission of flying, it's a matter of minutes. The longer time part on this mission is scanning the object. It may take a few hours if it's a large one. The largest church we scanned was very complex because it had a lot of columns, and it took us 5 hours. So it might be quite a long time process, but this is also because we made the model super quality because we wanted to pass this to the church administrator. Because of the lighting conditions in churches, we did not go the way of visual slumps and went for the lighter slumps, which we find more robust. But we are experimenting with visual odometries and visual slumps in other of our projects. But I have to say this is one of the research fields where our group does not have so strong participation. So visual slumps is something we are moving to, but slowly. So we are staying so far with laser slumps. We use optic flow as a visual odometry. We use this for backup if our laser odometry somehow fails, for example, to be able to stabilize the UAV. We can fuse
laser slam and visual slam all at once by our fusion algorithms. This is also open source. The description is available in the papers, so you can find it on our web pages if you would be interested.
So there is a question, and it's regarding that when a drone is approaching a point for documentation, it hovers for some time. And the question is if the delay is pre-planned to stabilize and take a picture from that point, or it's the attempt to reach the exact point, like some low speed slowing down. You are right, you've seen the correct effect, and you guessed it also right. We have there a slight delay which we can specify to hover at the point for some time and to take a few more pictures. Here the delay in this hovering delay was set quite high. It was something like 10 seconds because we wanted to show that we stay in those positions and that we are taking pictures. In reality, this is quite low because we know when we want to take the pictures. So we just go there, we stop, hover, take a picture and go. So the delay is not that big. It's a matter of 2 seconds, for example. Because we also need some time to stop the drone when we are moving from point to point, of course. So the pictures are not blurry, for example. So thank you for participating or for listening for this live demo. Hopefully it was at least interesting to see it work in real time, even in such limited conditions.
Okay, so hello again. We are sorry for a slight delay, which was caused by finishing of experiments for the media. And now I would like to introduce you Milan Škobrtal, who is from the National Heritage Institute, and he will talk about the project Dronument from the historians and restorers' point of view. So now it's your turn.
Thank you. Good afternoon. As was said, my name is Milan Škobrtal from the National Heritage Institute, regional branch in Olomouc. And I'm here to briefly tell you about some goals which we achieved in this project with the point of view of the conservationists. So, please excuse my English, and here we go. One of the conditions of providing professional care of historical monuments is a quality survey of its technical conditions before the adequate renovation or restoration will begin. Besides of the chemical technological analysis of studying of historical photographs, archival documents such as plans, receipts, sometimes descriptions or correspondence, is documenting of monuments one of the keys to preserve ours and also world's cultural and historical heritage. Our research is mainly focused on photographic documentation of parts of historical interiors with limited accessibility. Basically, it's about high church naves or representative halls of chateaus. We want to simplify, put more precisely, and speed up the process of documentation because we don't need a scaffold or lift track to get to the interior parts, which are, for example, high under the walls. We aim our photographs on artistic decorations such as mural paintings or stucco, but we have also documented static crevices or, for example, high altar in the Holy Cross of the Holy Cross in a church of the elevation of the Holy Cross in Prostějov on the pictures. We were asked to do that because members of the parish weren't able to reach that high, and also they weren't sure about the state of preservation of the altar. Our photos proclaim relatively good technical state of the canopy. But probably the two most important monuments of our research, which I want to tell you about, became Pilgrimage Church of Saint Anne and Saint Jacob the Greater in Stará Voda u Libavé and the Provost Church of Saint Maurice in Olomouc, which along with the Chateau Blumlov was picked to be scanned and then turned into 3D model with annotations. The main parish church of St. Maurice in Olomouc is one of the most important late Gothic monuments in Moravia. It was built in stages between 1412 and 1540, and it was built on the place of an older church. Detailed laser scan of interior, which was made there, serves as a basis for mentioned 3D model with texts and photos describing its artistic items. In 40 annotations, you can read about construction and history of this three-aisled hall church, its walls, altars, paintings and sculptures, or about the organ, which is the biggest one in the Central Europe. It has almost 8,000 reed pipes. But the major part of the annotations is about the neo-Gothic stained glass, or vitrages in high late Gothic windows with tracery. This stained glass is about to be restored, so we gave them the most of our attention. Colleagues from Czech Technical University made detailed photo documentation of each vitrage by our octocopter. These photos were merged together to the photo maps of whole windows, which can be zoomed to the close-ups. On the left side, you can see the whole photo map of the stained glass window, and on the right side is detail of this photo map. It's a head or bust of Saint Francis from Assisi. Restorers can see details of the glass and defects in context of the whole stained glass window. Advantage of our method is the tradition over the traditional documenting from the ground is elimination of deformations of the image because caused by the view from the below. This is especially related to the upper parts of the windows. Our photo maps are captured in horizontal level and approximately from 3 meter distance, which is also beneficial for quality of each picture. 3D model of interior of the St. Maurice Church in Olomouc will be posted on our website, dronument.cz, during this September, the whole one. Its verses will be available in Czech, English, and later German language. Mentioned Church of Saint Anne and Saint Jacob the Greater in Stará Voda u Libavé is an old pilgrimage site with tradition dates back to the 15th century. Current Baroque church was built during 1680s thanks to the Charles II Liechtenstein Kastelkorn, Bishop of Olomouc. This ambitious project was created by Giovanni Pietro Tencala, North Italian master from Ticino region and imperial architect. From the Ticino region also came painters and sculptors in sandstone and stucco. But oil on canvas for the high altar, oil painting on canvas for the high altar, the bishop ordered in Rome through his art agent. Bishop Charles charged with administration of the pilgrimage site the Piarists and built for them a cloister with college. The site was administered by the Catholic Church till the deportation of Germans from Czechoslovakia, from Sudetenland after the World War II. Then came Czechoslovak People's Army and then Soviet Red Army, which devastated the church and let disappear the abandoned cloister and the village. Recovery of the church came after the fall of the Iron Curtain. Our documentation works in Stará Voda were focused on damaged stucco and wall paintings, except the vault because ceilings are better accessible for making photos from the ground. In this case, the restoration works aren't currently planned, but our photo documentation can serve in the future if the degradation of the art items would continue. The projectile octocopter is the most useful here in case of the 4 paintings under the octagonal vault, as a device of making photos or as a carrier of a headlight, illuminating the motif while pictures are simultaneously made classically from the ground. This cycle, largely degraded by the rainwater, depicts themes from the life of the Virgin Mary and Christ. For example, thanks to our research, were identified details of the Annunciation scene. This is what you are looking now, and I will describe it for you because it can be hardly read. Here is the Virgin Mary kneeling on a knelt with the open book. In front of her is sitting on a cloud, Archangel Gabriel, holding the lily, symbol of purity, in his left hand. And by his right hand, he's pointing up to the dove of the Holy Spirit. Over the Virgin Mary and over the Archangel Gabriel are angels in clouds, here and here. Here's a group of 2 angels. One is here, this is his face, looking at the other one and pointing at Archangel Gabriel. You'll see it better on the next panels. The second one is, here is his face, and he's looking down, and he has clasped hands for praying. And here is a little baby angel or puto on a cloud. This is where you can see better those groups of angels. Here is the one pointing at Archangel Gabriel, looking at the other one. His head is here, and he has clapped hands. Here's the second small angel. Here is his head, his body, right hand, right leg, left leg. Right hand is here, and the left one is pointing up to the dove of the Holy Spirit. Just recently, we've managed to find a pattern for this wall painting in Stará Voda. It's an oil on canvas by Louis de Boulogne-le-Jeune, or the younger, or the junior. This painting from 1710 is probably created for the chapel of Virgin Mary in Château de Versailles. And we can see a small variation of composition of Gabriel and Virgin Mary. Here is Virgin Mary also kneeling, but Archangel Gabriel is on her side, while in Stará Voda they are face to face. Here is the group of angels. Now, when you see the original, you can maybe better imagine the paintings in Stará Voda. And here is the baby on the left side, and here is another puto or baby angel, which maybe is and maybe isn't is in Stará Voda also. The puto or little angel is lying on the cloud, half lying, half sitting. His legs are down, right hand on a cloud and left hand pointing up to the dove of the Holy Spirit. And these groups of angels, you can see it better here. Pointing angel on Archangel Gabriel, the second one praying. Here is the dove of Holy Spirit. They are very significant for this composition, and therefore we can speak about the influence of this painting in Versailles. And it's not about the direct influence, it's probably about influence through the books of engravings which depicts art items from the Chateau de Versailles. But we don't know that book, but this practice that famous art pieces were copied in regional centers is very common in the Baroque era. And here is the mysterious baby above Archangel Gabriel. Here is his head, left hand, right leg, and left leg. And here is drapery covering his tool. And here you can see the original piece. These significant figures, as I said, prompt the influence of de Boulogne's painting in Staravoda, probably through some book of engravings of artistic pieces, de Versailles, as I said. This hypothesis must be proved, but for now we can support it by the existence of inverse copy of de Boulogne's Annunciation from Église Saint-Martin-de-Ré in Normandy. It's here. As I said, it's reverse copy, and this group of angels is missing, but it's not exactly copy, it's a variation, but very, very close to the original one. And we believe that findings like this, which are in, or can be in eyes of art historian or conservationist important, can, along with the documentation method that we do, that it can help to better understand and better preserve cultural heritage in general. Thank you for your attention. Are there any questions? I don't see that. Nothing.
Questions from the physically present audience. So, if not, we will follow with the first presentation of the participants, which should be the long-term autonomous environment monitoring via 3D model alignment. So if I can ask Sia Benvir. That's fine.
Now we can start.
So, thank you for organizing the workshop. My name is Asia, and I'm a postdoc at the Visual Recognition Group here in the Czech Technical University. And before that, I completed my PhD in France in a robotic lab specialized in data-driven environment monitoring. And my research focuses on long-term visual inspection done with robots. So, to give you a bit of context on how to proceed with the inspection autonomously, we saw that there is first the data collection that is done by robots. The second step is the data representation. and the final one is data comparison. And all of these steps can be done autonomously. And this has the advantage of having a high repeatability, as this was mentioned this morning, but also the advantage to process a large volume of data that could not be done by a human. And my work focused mostly on the data representation part and the data comparison. So I assume that the data was collected already, and I do not actively intervene in the data collection as is done, for example, in the previous projects that we saw. And to give you examples of the kind of comparison that I'm looking at, here is an example of a lake shore next to my previous lab in France. And the kind of environmental changes that I'm looking for is not necessarily the seasonal one, but for example, knowing whether a tree is still there or not, or if there is more vegetation than before. And another type of environments that I look at also is urban structures over a long period of time. So for example, after or before a renovation, and to observe what changed. And the typical pipeline that I go through is that at a certain point in time, I scan an environment using a camera only. So I rely on image information. And here you can see a point cloud representation of Staromyskie and Namiestie here in Prague from images only. And the advantage of this representation is that it can store both the 3D information. So you have size, you have depth, and you have geometric constraints about this environment. And I also store the semantic information. So this allows me to know whether there's a statue somewhere, or there's a window, or other human recognizable objects that are reliable for inspection. And in a later time, in future, let's say that I have this image 2 years after, and I want to know how it compares with the previous past that I had. And this goes in 2 steps. Usually, first, I need to recognize the place that the pictures was taken at. This is, in computer vision, this is a standard task called scene recognition. And the second task that I solve is to compare the image. And to do that, I first align the image with the previous one, and then I compare them structurally and semantically. And so for the rest of this talk, I will talk about 2 of my contributions for scene recognition and feature matching. And these 2 tasks, they rely on visual features. So just to be sure that I don't lose anyone, I will briefly explain what is a visual feature. There are 2 types of visual features, and they are numerical representation of the image or part of the image. So on the left, you see what is called a global feature, and it's a numerical vector that summarizes the whole content of the image. And on the right, what you see are local features, and it's also a numerical vector, but that summarizes only a part of the image. And these 2 are what I use for the inspection. And for the scene recognition, this is usually how it's done. So you have on the top the image that I'm currently seeing at time t, and this is the query image. And at the bottom, what you see are what are called the database images. So the images that I collected maybe 2 months ago, a year ago, and etc. And instead of keeping these whole images, what I'm going to do is that I'm going to compute this feature that is a summary of the image. And so next time that I will want to compare this query image with one of the database images, I will just compare their numerical representation, because it's much easier to compute the distance between these images with just an L2 norm rather than comparing the whole image. And this allows me to retrieve the most similar image against which I will have to compare for the inspection. So now that I have 2 images that represent the same place at different times, I want to compare specific regions between the images, and for that, I will use local features. And here, once again, I'm going to use the numerical summary of the image, that are these colored vectors, and to know which region of one image match the other, I'm going to compare the distance between these 2 vectors. So now that I have defined the main tool that I use, I will present my contributions. The first one is on scene recognition using semantic and geometric cues. Here I'm briefly showing the state of the art for place recognition. And on the left, what you see is an image where these local features are computed from the image appearance, so the image light and the image colors. This is what I call pixel statistics. And this works very well, especially in urban environments, but for natural environments as this, where there is low texture, a lot of repetitive patterns, this does not work well. So the next step is to use semantic statistics. For example, here you see the sky in blue, the vegetation in green, and the lake in purple. So you get a better understanding of what the scene contains. And my contribution is on the use of semantic and geometry. And for this, I propose to use semantic edges to generate local features and then to summarize the image. And the motivation behind this is that if you look at these images taken at the same place but at very different seasons, and on the bottom, if you look at the semantic edges, you can see that humanly there is enough information to understand that these are the same place. And this is quite resistant even to changes not only of seasons but also of weathers, and even when you have light artifacts such as sun glare. And so my approach is to get the image, extract the semantic edges on the right, and gather local features on specific positions of the semantic edge and aggregate them into a global summary of the image. The limit of this method is that right now I'm using only coarse edges. So for example, if you look at the image in the middle, you can see that it has much less information than the rightmost image that has more edges. And currently I'm not exploiting these finer edges, but this would be very useful for images such as this one along a road, because when you go along a road with the car or any other system, it's usually always the same. You have the road on the bottom, the trees, and then the sky, which is not very distinguishable even for us humans. Whereas if you use this kind of finer geometric cues, you can maybe distinguish between very repetitive scenarios. So this is my work on the semantic place recognition. And now I will go towards object-guided feature matching. So this is for the part where we try to align specific regions and even specific pixels between images to be able to compare them. And so here on the left is what we would like to achieve. So here I'm showing pictures of two buildings in the city between night and day. This is the kind of pixel matching that I would like to achieve so that I can compare the structure. And on the right, this is what is currently achieved by the state-of-the-art local features. And the main issue is that all of these features, they rely on the appearance, which is color and light. And this is not, and the changes here are too strong to be, for these features to be robust. The one thing interesting about this is that you can use objects that are easier to detect even across strong variations of appearance. And so here I'm relying on the very systematic window distribution that is a very strong visual signal. And I'm proposing to match these windows, which can be done using only geometry because there are always rows of windows next to each other. And once I know that the windows on the left side of the building match the one on the left side and the ones on the right side match the one on the right side and they correctly align, I already have a kind of coarse signal of what image regions in which region in the first image match which region in the second image. And this allows me to have better pixel alignments later on. And this is what is done here. And the way I go is that first I have to detect objects. So here I'm showing examples of how to detect windows because the application was on cities. And in cities, the windows are the most frequent objects to use. And the next step is to match these windows. And I do it in a very intuitive and a very human way, is that I try to match one window to another. And I see the if the neighboring windows also match. So here you see on the left side that they align well if I match this one. And if I matched this incorrect windows together. So you can see here on with the two windows highlighted in blue. This would give me a shifted alignment. So I know that these windows should not be matched together. And once this is done, you can then use the geometric properties of these images and the geometric properties of the scene to later match the pixels. And I'm showing some other qualitative results that are quite impressive because they show that they resist to not only the illumination changes, but also the obstacle and the occlusions that you can find in dynamic environments. And the future work on this is that I've shown these results on CT images, where you can reliably detect explicit objects or objects understandable by humans. And so the next step of my work is to apply this to natural environments where you don't have objects as explicit as windows and statues to match together. But you can see that naturally you are tempted to match that little red highlighted tree with the little red highlighted tree on the right image and the blue one, and do the same with the blue one. And this gives you already a coarse matching signal to compare the images that you can later refine. Whereas if you used only local features, you would never be able to match these two images because they are too different in visual appearance. So thank you for your attention. And this is all. And if you have questions, feel free to ask. Yeah.
This is evolving for navigation of drones or basic navigation. I'm not technically.
Yeah. So I think this comes after the step of navigation. So here I assume so that in this case it was a boat. The boat already went to collect all of the images, and now I cannot conduct the boat to collect more images. I have to do them with what I have. Whereas I think the work that they do here is that they direct the drone specifically to the location that they want, so they can they can control the way they will collect the images. And I assume that this is not the case here. So this comes after. Does this answer your question?
Okay, so welcome back at our workshop. And now, if Mickey is prepared, I ask him to start his presentation.
Yeah. Can you everybody hear me okay?
Yes, we can hear you well.
Cool. Well, thank you very much. I've been finding today's workshop really interesting. Yeah, so thank you very much for putting everything on. So my name is Mickey Lee, and I'm about to be a final year PhD student at the University of Bristol in the UK. Today I'm going to be presenting a bit of my work on the topic of sort of planning for failure, providing guarantees for multi-robot mission completion despite robot failures. So all of my sort of safety and comms questions come from that sort of angle. In particular, in the context of multi-drone inspection missions. So this work is jointly supervised by my professor, Arthur Richards, from the Bristol Robotics Laboratory, and Professor Mahesh Siribandara from Toshiba Research. Cool, yeah. So in my work, as I said, I've been focusing mainly on multi-UAV systems, in particular how individual UAV failures affect the reliability of mission performance. So ensuring performance with respect to time constraints and external risks is a really common requirement in real-life planning. This is especially true in aerial robotics applications, where drones themselves are possibly prone to failures, so mechanical failures, battery, communication, and so on. Of course, one method of mitigating this risk is through the use of multi-UAV systems, which have the potential to be more flexible, scalable, and failure tolerant. However, this comes at the cost of more challenging coordination, especially if failures occur. where a lot of current task allocation methods typically seek efficient division of labor for early mission completion. So just to give an example, consider the inspection of a railway bridge with multiple UAVs, where the priority is to avoid disruption to services, requiring reliable mission completion before a really hard deadline. So in this case, the passage of the next train. So like the traditional solution found with a multi-agent coverage path planning solver would be to divide the work into partitions between the UAVs, like the following, where each drone is tasked to inspect a single portion of the bridge. The division is done such that the cost, often travel time, or energy usage is minimized. But crucially, this minimization implies that each location is only really visited by one agent. However, as we see here, UAVs are failure prone. And if any one of them fails, other UAVs have to be reactively rerouted to visit the missed tasks, possibly exceeding the deadline. So the question arises, if drones are going to fail, can we still provide some guarantee that the mission will be completed by the deadline? So our work says that providing such a guarantee is indeed possible. So by modeling drone failure probabilistically, for instance, by assuming a constant failure rate, or maybe something like a bathtub curve, which models a product life cycle. So if these failure models are known, we would like a path plan which could maximize the probability that the mission will be completed by the deadline, regardless of actual failures. So practically, optimizing for this objective can reproduce time minimizing paths from normal coverage path planning, but only if it actually improves the probability of mission completion. On the other hand, slower path plans might actually be chosen if a greater probability of mission completion can be obtained. So we refer to this whole problem as the reliability-aware multi-agent coverage path planning problem. Yes, a mouthful, but it's a good acronym, I think, which seeks to maximize the reliability metric of probability of completion by a strict deadline. So, yeah, so my work is all about this. So it's to find solutions to the reliability-aware multi-agent coverage path planning problem, where the goal is to find paths for each robot which maximize the probability that every part of the environment will be covered by a specified deadline. So this differs from multi-agent coverage, which solely seeks to minimize travel costs or energy usage with no task revisiting or failures. This also differs from works which employ sort of reactive failure strategies, which trigger when a drone fails, as we a priori want to find maximum reliability path plans, while also giving a quantitative value of the probability of mission completion. So I can say to the contractor, this mission will be completed with a 99% certainty within the next 2 hours, regardless of whatever happens. So to summarize sort of the key contributions of my work, so I've introduced this RAM-CPP problem and developed an algorithm for computing the probability of mission completion as a starting point, as a reliability metric. So most recently, I have extended this to allow for planning in continuous time, as well as supporting asynchronous movement and tasks of varying duration. And secondly, I have developed a number of optimization methods of varying accuracy and performance for solving the RAM-CPP problem. So today I'm just going to introduce one of them and some results. So the most recent addition to the set of methods which can solve the problem is this greedy genetic algorithm. So this algorithm seeks to iteratively find a single path for each agent. Then in each of these iterations, a genetic algorithm is used to generate the single path for a single agent, which maximizes the reliability of mission completion given previously found paths. So this algorithm is greedy because it just tries to choose the best option each iteration, hence the name. This is in comparison to previous methods, which attempted to simultaneously find the optimal paths for all the agents at the same time. And this doesn't really scale so well. To demonstrate the results of my methods, I'm going to provide some comparison between a couple of following methods. So I have some other methods which do this whole simultaneous optimization, and there's two objectives there. One variant tries to maximize only probability of mission completion, and the other one sort of a weighted sum of probability of completion and earliest completion time. I also compare it to what I call partition methods, which are essentially the traditional multi-agent coverage path planning, divide the area equally between the agents. This uses sort of k nearest neighbors to partition the environment. I've also implemented a sort of basic overlap partition, which schedules the neighbor's partition after completing its own work. And finally, we use random walk as a baseline. In addition, the RA-MCPP solver is agent failure distribution independent, so I can plug any agent failure I want into it. So for this particular evaluation, we use what's known as the bathtub curve to model the lifetime of a UAV. Essentially, the bathtub curve is a mixture of 3 viable distributions, modeling early failure, random failure within its lifetime, and the end-of-life failures. Then these methods are evaluated on 3 sort of realistic scenarios. 2 are viewpoints sampled at different resolutions from a 3D model of an aeroplane, producing sort of paths like this and like this inside AirSim. And the third scenario is of the robotics laboratory, where the nodes were handpicked, inspected with 3 drones. And the deadline for each scenario is set to the time for one agent to traverse a tour of the environment. So the bar charts here show the probability of completion of the strategies found by each method on the environment. So our greedy genetic strategy found a solution that is almost certain to complete and is better than the other methods, which are the sort of the 2 variants of the genetic algorithm, which attempt to simultaneously optimize, and much better than the sort of environmental partitioning methods, the original multi-agent coverage path planning methods. And in each of these scenarios, our methods find path plans with greater reliability. So just to give a bit more of an idea of what's going on. So here on the left, we show the paths that are generated by the genetic algorithm on each environment. And on the right, we show how the probability of completion changes over time for each of those paths up to the specified deadline. So a couple key things to notice. Here, we see overlapping paths between the 3 agents. And this is reflected in the fact that the probability of completion over time increases. And secondly, it's also clear that sort of relaxing the requirement to finish as early as possible can eventually allow for greater reliability by the deadline. Cool. So just as I find you guys' drone sort of infrastructure really interesting. So one of the next things for me to do with my own project is essentially to test my path planning algorithms on real drones. And this leads me to my current side project of building a multi-drone flight capability for our flight arena in Bristol in the UK. I thought this might be interesting to add for some of you. So in particular, we're looking to use cloud technologies to support scalable and extensible platforms as a scalable and extensible platform for myself and others in the flight arena and the flight lab to use. So we're looking at things like containerization technologies such as Docker, which help to encapsulate drone development environment, allowing for drone agnostic development of controllers. And then things like container orchestration technologies such as Kubernetes, which you may have heard of, which are in industry, they're used to deploy sort of applications to a cloud cluster, compute cluster. But in our case, if we treat the cluster as a group of drones, because each drone is essentially a flying computer, then we get multi-drone support and we get networking, as well as stuff like failure recovery, purpose-built user interfaces, and all sorts of other things which are already available to us, helping to deal with a lot of the sort of underlying network nitty-gritty. So this may seem like overkill, but one of our core goals was to simplify the user experience for those who want to experiment with UAVs, but don't have the necessary experience or background to do that sort of thing. So with our system, hopefully, the user only needs to develop the controller module and doesn't need to worry about networking or drone hardware specifics. They can just go to the flight arena, upload their controller code. It might be a trajectory follower, might be something more lower level, and literally just press go, and hopefully things will work. Cool. Well, thank you very much for listening. Hopefully that has been interesting. It's slightly different from what's been presented today. But if you have any questions, please either ask now or contact me at the email. But again, thank you very much to the workshop organizers. Cool.
So So thank you, Miki, for your interesting presentation. And are there any questions for the physically present audience? So there are no questions. So thank you again.
Thank you very much.
I would like to invite the last presenter today, which is František Nekovář, with his presentation on multi-tour set traveling salesman problem in planning power transmission line inspection.
Okay, can I begin?
Yes.
So, good afternoon, everybody. My name is František Nekovář, and I'm from CTU in Prague, and from Faculty of Cybernetics. And I'd like to talk about my recent paper, which is, as you heard, the MSTSP problem in power transmission line inspection. So, quickly about the motivation which we have. So, the electrical companies, and especially companies which take care about power transmission infrastructure, invest a lot of money and time into keeping that infrastructure working. So into maintenance and into inspection of the wiring. And typically this is done using manned helicopters and manned professionals, which inspect and work on a live wiring. They do not get shut down. This is both kind of dangerous and expensive. And what we would like to is present an alternative, in this case, the alternative to inspection, which could be done both unmannedly, without people, and then autonomously. So the complete autonomous unmanned inspection. And UAVs are suitable for that, especially multi-rotor UAVs, which we at our lab work with. And our challenges when we work with UAVs is the limited battery time. It's the interference from the live wiring, which requires additional shielding, and it's possible obstacles in inspection area, since typically power transmission lines are, for example, present in forest corridors or in settlements, in villages and cities. So that should be taken care of too. Our idea then is to somehow formulate this inspection problem as a variant of a well-known traveling salesman problem. I will just shortly talk about that later in future slides, and then propose some way to solve this problem and present working plans, working solutions, which could then be fed straight to some UAV controller, which would then execute the plans. So shortly about the traveling salesman problem, since not everybody present might be an engineer. Typically, with the salesman problem, we would like to visit a set of cities, and while we visit all of them, we would like to cover the shortest possible route. Like we could go zigzag here and there, but that route would be longer than this one. We call the shortest route optimal route, optimal with regard to distance. Then one of the generalizations of this problem is multi-tour TSP, which uses multiple salesmen, so multiple agents originate their tours and end their tours in the same depot, in the same node, but each visits different set of cities. And the added distance of all the visits of all the tours is minimal. And then there's a third generalization, which is called a set TSP, or sometimes in literature, just generalized TSP, in which case the cities are grouped into sets, and we just need to visit one city in each set, while also keeping the distance minimal. And essentially what we came up with was combining both of these generalizations, so that's the multi-tour set traveling salesman problem. Why? So this, for example, on this map from OpenStreetMaps is Nechranice substation. It's probably one of the biggest substations in Czech Republic, probably the biggest, but I cannot be sure about that. And about 30 to 40 power lines originated there. And in an area of about 5 kilometers, which in a radius of 5 kilometers, which you can see on this map, there's about 200 different power line segments. When I talk about a segment, I mean a wiring segment between two specific pylons. So this area then is our typical working site, and it was suitable for our evaluation, which we did there. Our representation in the beginning is very basic. We have some pylons, right now 4 of them, pylon A, B, C, and D. And it takes our UAV, which originates in one depot, some time to travel to a pylon. It takes some time to inspect a pylon. It has to, for example, the UAV has to fly very slowly, and since it's monitoring using a camera, so we can get a good image. Then it has to traverse to a different segment and also visit a segment. This formulation is easily to understand. It's quite easy to understand, but it's not suitable for planning because it would be terrible to formulate. So we kind of do a little mind game and reformulate it. And this is the set TSP itself, because right now a segment on a power line can be inspected in both directions. We can go from A to B or from B to A. But once we inspect it, we don't need to visit it in the other direction anymore. So that's why we represent inspection in both segments as a set. So for example, here is the inspection of first segment in direction A to B or B to A, and then second segment from C to D to C. And once we visit that node, that set, we do not visit it anymore. So the graph which we work on is a little bit less messy and easier to solve in the result. And then finally here on the bottom is the little math that formulates the problem. We would like to minimize the total inspection time, denoted as T maximum, for all the tours in a complete set of tours, and for all the sets I, which contain some vertices. And these vertices, which are the visits to some segments, are grouped. So we propose two solvers, two very specific two solving methods to this problem. First is a solution using linear programming. Linear programming is very good, and it's commonly used for obtaining optimal solutions or close to optimal solutions. I mean, the optimization method doesn't guarantee optimality, but we pretend it does. And the formulation is quite complex, and it takes a lot of time to solve. So it's suitable sometimes it's suitable and it's practical when we know the environment and, for example, for the substation, but it's impractical if some failure happens or if we need to come to unknown environment and make the plan on site. That's why we propose a second solver, greedy random adaptive search procedure, which was inspired by meta-heuristic solvers, which we also work here with at the CTU, which uses the greedy random procedure and then adaptive tabu search. Even though this procedure doesn't guarantee optimality, we have proven when evaluating it numerically that we can achieve about 10% error from the optimal solution from the linear programming. And while the linear programming takes about days to solve, greedy random adaptive search procedure takes about minutes or even seconds to solve. So it's much more practical on site. We have evaluated these solvers quite extensively. Evaluation was performed on the Nechranice substation and its surroundings. I can show you the example plans. This, for example, for a radius of 1 kilometer, we can see the individual UAV routes, and this can be solved with the linear programming quite fast. But for example, with radius of 5 kilometers, we already have hundreds of individual segments, and this plan took about a day and a half for linear programming to solve with Cplex solver, while our meta-heuristic solver solved it in about 7 seconds. And here, to put it into reality, this is the map, and this is kind of the overlay of the possible routes which we have planned for. So these are the 5 kilometers. And so for the future work, we would like to account for the weather, since weather and wind conditions have a very specific influence on flight performance and on battery time. Right now, we have just been accounting for the total flight time, but actual battery time is more important than flight time, because, for example, if we fly opposing to the wind, we will consume more power than if we fly along the wind. So some segments in some direction might not even be inspectable during wind conditions. And we would also like to account for possible failure modes, because a battery might fail, the capacity might not be specified before the flight, or some UAV agent might fail and another route might have to take over. And that's why the grass solar is important, because we can do this replanning on site. Okay. So just for the end, I would like to thank the Horizon project, the Aerial Core project, which inspired this research, and check the grant against for funding our research. Thank you. And that's it. So thank you for your attention. And if you have any questions. All right.
Okay, so if there are no questions, thank you, František, for your presentation. Okay. And according to our list of participants that wanted to present, this was the last presentation. Is there anybody who, for example, forgot to mark that he or she wants to present its own topic at our workshop during the registration? Okay, so if not, thank you for attending our workshop. And if you have any questions, you can ask now or contact us via the email, or yeah, it's probably the best way to contact us. You can find all emails at contacts at the mrs.felek.cz address. There is the list of the people. And if you would like to ask somebody from the National Heritage Institute, our colleagues in this project, we can pass the question to them or send you the contact. Okay, so thank you for your attention, and that's the end of our workshop.